Okay, good afternoon, folks. I have a few announcements. One is your average on the midterm exam is around 74, 75, which is not bad, but it's not as good as what you had in the first midterm was 92, 91, 92, something like that. But that is the nature of the course. And even for the final exam, it's going to get a little bit more complicated. I mean, in a sense, it's not complicated, just the extension of the formula. Formula goes from one sample to two samples for two means, one mean, and so forth and so on. If you know how to do for one, you should be able to extend it to two samples, two means, and so forth and so on. But can you guys hear me and see the image? Just one person says yes, then I'm okay. I don't see any. Oh, thank you. Good, good. Thank you. And the second thing is about the Excel. I was checking my previous recorded lecture, and I was kind of amazed that I couldn't see the Excel. And the reason I couldn't see it, the lecture I did about Excel, because it was a full screen. So if you make the screen smaller, and then you can see the Excel part too, my last week's lecture. I just wanted to remind you, in case some of you watch the whole thing in a full screen and you don't see the last part and you only see my sweater, but if you make it smaller, escape the screen and make it smaller, then you can see the Excel part too. Other than that, we have, including today, we have 6 more lectures left. And we have 3 more chapters to finish. And your Excel number 6 is there. You're supposed to submit number 5 today. I got an email after the exam grades changed, but they didn't change. I don't understand the question. What do you mean the exam grades changed, but they didn't change? What do you mean by that? Whatever they graded, that's your exam grade. They can't change it. Whatever your grade is, that's going to be it. I got an email that said the midterm grade was changed. No, whatever your grade was, that's I don't know who sent you the email, but the grade that you got for your midterm, that's it. That's your grade. Eventually, at the end of the term, it will be, I think it's going to be graded on a curve, maybe 1 or 2 extra points each person will get at the end. Okay, let's start on the lecture. We are on lecture, chapter 21. So far, we talked about t-distribution. Remember, t-distribution is something that you don't know. Sigma is unknown. Sigma of the population is unknown. Not only the mu is unknown, but sigma is unknown too. And we did one sample mean in the was chapter 20, I think. In chapter 21, we are going to extend that to 2 sample problems, basically computing 2 means. And still, you're going to see that when I go through this lecture, I'm just going to compare back and forth with the one sample mean and one sample mean, and you're going to see the similarity, and the formula is just a little bit extended, including 2 samples. That's all. The rest of confidence interval or null hypothesis, all of these are exactly the same as before. Minor changes. Okay, let's get started. We are dealing with the 2 means, not 1 mean, 2 means. And let's start with an example because it's the same thing, the formula. You're going to see that when we go through this, the formula is going to be modified. So breakfast has long been thought of as the most important meal of the day and may affect students' performance in an academic environment. Two groups of Middle East students, middle school students, are selected at random and are given bagged breakfast each morning before their classes. The groups receive the same instruction at school, but group one is given well-rounded breakfast according to the FDA food pyramid, whereas group two is given a less wholesome meal. So that's the only difference. Below are the mean GPAs for each group at the end of the first school quarter. So we are comparing these two groups, group one and group two. Group one is well-rounded, isn't it? Yeah, it's basically well-rounded and less wholesome. Okay, when you look at it, this is two, you're dealing with the two groups. You have two samples, you have two sample standard deviations, two sample sizes, two populations. Populations are independent of each other, definitely. So now let's answer the question. Are the data matched pairs or from two independent distribution? Okay, right off the bat, you can say that it's not matched. 51 versus 47, there is nothing that you can pair these. There is no match. So not matched, basically. Not matched pair. Okay. Another way of saying it, when we say that whenever you want to match pairs, have matched pairs, that you need to have a way of pairing two individuals or your sample data or sample or the people that you pick. So basically there is no consistent here, no. I mean, right here you can say it's not, but if you want to extend and talk about it, that what do you think of a matched pair in general, and you need to have a consistent and meaningful way to connect individuals between the two groups. And even if you have these two the same, but you don't have, you don't know who's pairing with who, that means it's not matched pair. You have to have way of pairing people. Like for instance, if you want to have it something, we can have two groups here. Let's see. I'm going to put two groups here, group one and group two. Say group one is Abby, Mary, Ellen, and so forth and so on. And this side is Mike, Aaron, and who else? Alex, and so forth and so on. So when these are matched, you know which one is going to who, how are you matching these, then this becomes match. And of course, the numbers, they have to be the same number. And but here, not only the numbers are not the same, so therefore you can say N1 is not, N2 not the same. You don't know who's doing what or who's matching with who. Okay, that's the first part. Now the definition. For strict adherence to guidelines in performing a two-sample t-test, testing the difference of two population means or confidence interval we need the following characteristics in order to get valid results. Remember, when we are talking about two means, previously in the last week's lecture, we dealt with the one sample. So all we are going to do, we are going to do exactly the same, but instead of having one sample, we are having two samples. Instead of dealing with the two data points, we are going to deal with the difference of the two samples. So again, it becomes kind of a one sample because you're looking at the difference. At every step that you're looking at, difference in population, difference in sample, difference basically, that's the, I mean, that's part of it. That you're going to see that if you get the idea what we are doing for the two samples, it's a difference in the population mean. So it's going to be difference in sample mean, and when it gets to standard deviation, is a little bit different. You're going to see what happens there. Okay, so in order to have this two sample mean, you need to have both of the samples must be SRS. That means they should be randomly picked. Both distributions are normal or kind of close to normal. Samples must be independent of each other. That means they should come from independent population too, independent of each other. Different individuals and no consistent, reasonably way of pairing individuals between the samples. Okay, now this is what I'm talking about here. It says a confidence interval for the difference of population we are looking at it. So therefore, you're going to have difference in the means of the samples. If you recall that for one sample, let me write it down. You're going to see that I'm going to use this and get to that formula. In one sample, we had X bar plus or minus T star. We had S over square root of N. I'm going to write this one in a different format. So because the reason I'm doing this because I want to extrapolate this formula here. I can rewrite this one as X bar plus or minus T star, but I can square this and put it under the radical or square root. So that means this is the same as square root over N. This is for one sample, right? Now, if we move to the two samples, here's the two sample. Since this was for 1 mu, we calculated for 1 mu, 1 mu. Here we are calculating for difference in mu's, two different population mu's. So therefore, instead of having X bar, you're having the difference in sample means, because this is a difference in population mean, so you're having the difference in samples. So the percentage over here, 90%, whether it's for one sample or two samples, that's going to be the same for both of them because you're using the difference. Here what we have, in one sample, you had standard deviation squared divided by n, the whole quantity under the radical, the square root. Here, you're going to say, this is going to be due to sample 1, similar to that. You put 1 there, subscript 1 represents group 1 or sample 1, plus subscript 2 for group 2 or sample 2. That is the difference, that's all. So this is a for two sample mean, and that was a for one sample mean. And you can see that you can extrapolate from here. If you're calculating for the difference in population mean, so you should have the difference in sample means. So T star is going to be the same T star. And here because this is a positive number, so you are having this one as a standard deviation squared divided by a sample size for one sample. So you're having it for two samples. You've got to add that. That's it. So this would be, you can use this one for confidence interval, and we can do that. We can calculate that. In this case, let's just see what these are. This is x1 bar minus x2 bar. We can call this one, this is the estimate. This is basically an estimate of mu1 minus mu2. It's the same thing. X bar was estimate of a single sample. It's the estimate of population from one sample. Here's the difference samples. This is T star is still called critical value. What did we call this? We call this one standard error. We're going to call the same thing. Okay. Here in the one sample, we had 1 degree degrees of freedom, right? In this case, for this one, because each sample has its own degrees of freedom, therefore degrees of freedom is going to be between these two. So you take the sample size, you subtract 1. That would be degrees of freedom for sample 1. Take sample size, size of sample 2 and 2, and subtract 1 from that. That would be degrees of freedom for the second sample. But you will pick the smallest of those two samples, those degrees of freedom. Okay, suppose let's calculate here. What do we have here? Let's see, for this problem, degrees of freedom would be min. What is N1? If you look at it, N1 is 51. 51 minus 1 comma. N2 is 47 minus 1. So this becomes min of 50 and 46. So therefore, degrees of freedom would be 46. Okay. So all you do, you just in this form, just pick, just find degrees of freedom for each one and just pick the smallest of those two. That would be the degrees of freedom for the problem, entire problem. All right. Okay. I mean, knowing that formula, you should be able to even fill in all these things on your own because you've done confidence interval, you know how to calculate that. Instead of using one sample information, you're going to use two samples information. But let's do it, and you can see that you already know this. Confidence interval is equal to, we said that we are going to do it for the difference. That would be x bar minus x2. It doesn't matter. You need to be consistent. If you're picking x1 bar minus x2 bar, keep it all the way like that. If you're using x2 minus x1, that's fine too. But be consistent in the entire calculation. Plus and minus, you have T star, this is the formula we're using, S1 squared over N1 plus S2 squared over N2, and that is the formula we have. I'm going to write the information from this here. We have, and it will be easier to substitute the numbers here. So we have x bar 1 is 32, x bar 2 is 3.2, sorry, 2.8, S1 is 0.77, S2 is 0.436, N1 is 51, N2 is 47, and mu1 is unknown, mu2 is unknown. Okay, now, so what do we need? First, we want to find this T star. Again, I'm going to go back here and show you one more time how to calculate the T star. And also, I will mention how to calculate T star using Excel. Although I mentioned it last time, I will go through that one more time. Let's go through this. So we know our degrees of freedom is what? Let's write this down. Degrees of freedom is, it was 46, wasn't it? Like from last page, you got it 46. So, but remember, we said that if 46 is not on the page, on the table, what do? We'll go to the next lower one. So if you look at it here, we don't have 46. We have 50 and 40. So therefore, we got to pick 40. We pick 40, right? And we pick 40, and it says 90% confidence interval. So this is going to be 90%. So degrees 40, and we go all the way to 90%. 90% would be here. You see that? That's 90%. If you go all the way down here, we put it on 40. That would be 1.684. 1.684. So T star from here, we have T star would be 1.684. Is everyone okay how to get that T star? Because that's going to be in the final exam. You got to know how to do those things. And if you wanted, I can draw something here, but we've done this before. If you're okay, I can skip it, but if you're not, then I can draw something here. Why did you say the degree of freedom is 46 and not 50? Because it says, if you look at the definition, it says minimum of those two numbers. Minimum of 46 and 50, it's 46. Smaller of those two. Okay? So are we okay with the T star, everyone? I want to make sure that you guys know these things because they're going to be in the exam. You're okay. All right. Now, for, yes, good, thank you. So if you want to use this in 90%, now I'm going to show you how to calculate this in Excel because you're going to have Excel programs to do these calculations. Remember when we say 90%, so if you draw the curve, normal curve, and here's 90%, so you have 5% here and 5% here, right? So if you want to calculate the same T star using Excel, you say T star, this is just a star, nothing. But in the cell, if you have Excel open, you just put this one there and you're going to see that you get exactly, almost exactly the same as this number. If you open your Excel on your laptop while you're watching. Here what we are going to do, we're going to say equal sign, and then you're going to type T dot imb. The minute you type T, it's going to show you others. Pick T dot imb. In here, you have probability and, I believe, degrees of freedom. So probability would be, because this is going to be T star here, and this is going to be minus T star, whatever the T star is. So if you want to find the probability of this, what would it be? It would be the entire this area. If you want to look at this part, it's to the left of this, because you want to know what T star is, you need to know this would be to the left of this. We've done this before. To the left of this would be what? 90% plus 5%, so that would be 0.95. And of course, we picked degrees of freedom to be 40. In Excel, you can pick 46. You get the answer too, but if you want to match your answers with what we got here, 1.684, if you put 40 there, you're going to see that you reproduce this number. That's how you do it in Excel. There is another function in Excel that it's T without a dot. You can use that, but that is used for if you have this curve again, 90% here. So you have here, this is 0.5%, 0.5%, right? So, I mean, 5%, 5%, it's not 5% and 5%. This is 9%. So you can use that function too, but that function only works when you add those two areas. Not basically what you can do, you can say T inv, there's no dot here, and these together is 10%, that's 0.1, and then you write degrees of freedom here. You get exactly the same answer, and the answer is going to be somewhere like 1. I did it the other day, 6835, and the same thing goes here, 1.6835, and that is T star. Okay, that is for Excel. You can use in Excel. But let's go back to this problem now. This problem, we want to calculate confidence interval. So all we have to do is just plug these numbers here. We already found that what T star is, and the rest of them are given here. So therefore, confidence interval would be equal to, so X bar 1, that would be 3.2, minus X2 bar, that would be 2.8, plus or minus, that's that part. T star, we calculated it's 1.684 times square root of, so you have first standard deviation, so the Excel input, and what did you get, 40? Okay, 40, I put 40 here because I wanted to show you that this answer is almost the same as this one. In Excel, you can put 46 because Excel can handle 46. Excel, any degrees of freedom you put there, Excel can handle. The reason I did this because I wanted to show you that this formula, when I use this formula, I put exactly the same thing that I got here. If I use that one, I get the same answer. Here for this T star, I use 90% and 42 on the table. I use a table. I just wanted to compare and see that, hey, we are getting the same answer. These formulas are great. All right, back to here. So standard deviation for the first one is 3.2 squared. N1 is 51 plus standard deviation for, oh, that's average, isn't it? Standard deviation is 0.77 squared. And the standard deviation for this one is 0.436 squared. And the N is 47. Web work, when you're using web work, you should use tables. But sometimes the, the tolerance of web work, it matches with Excel sometimes. So I remember in the past when I used to teach, when I assigned a web work problem, I talked to the web work server, and she was supposed to fix these problems. But each term, they're still having the same problems. You're going to see 1 or 2 problems they don't match. You need to let us know so we can fix the tolerance for that problem. So you should be able to. Another way of doing it, you may want to, if you see that the table doesn't work, just put the value in the Excel and see what the value is and put it there. It's more accurate. All right, so we calculate this as CI would be 0.4 plus or minus 1.684. And if you calculate this, I've done this, take square root of that, that's 0.12518. And the same thing we do. Confidence interval, you have a lower limit. So that means 0.4 minus that one, you got to times that. What is this value? I don't have that value here, but I did the whole thing. So you get 0.1892, and this one is 0.6108. That is the confidence interval. What does it mean? What it means is that if you look at the difference in the population mean, it's going to lie between these two numbers. That's all it means. Remember, in one sample, when we calculated the confidence interval, we said the mean of the population lies between these two numbers. Here we say the difference in the means of two populations lies here in between these two. It's the same, we're using the same vocabulary for both of them. The only difference is we're calculating for the difference. So I'm going to say 90% sure that the difference in GPA happens to be, here, I'm going to write it, happens 0.893. Happens to be there, right in the middle. Not right in the middle, it's between those two numbers. Okay, this was with regard to confidence interval. So you know how to calculate confidence interval using knowing sigma, then you use the z distribution for one sample. You know how to calculate confidence interval for t distribution when sigma is unknown. Now you know how to calculate the confidence interval for two distribution, two samples. You know how to calculate that. Now, again, in the past, we used the null hypothesis, alternative hypothesis for all those cases. We're going to use them here too. How do we start with the null hypothesis and alternative hypothesis? The first thing we did, we calculated the z value, calculated the t value. From there, we calculate the p value. Here we are doing exactly the same. Here we are going to calculate the t value for the difference, and these are, again, those standard deviation for two samples. So I'm going to write something here, one sample, if you can compare one sample test. In this case, we said null hypothesis, mu0 is 0, and we calculated t to be x bar minus mu0 divided by s over square root of n. Here we are doing the same thing, and the only difference is here when we write this, basically here mu is going to be 0 because we're calculating 0, and then you calculate the h sub a, whatever the condition is for h sub a, whether mu0 is greater than, not equal to 0, or less than. Right. We are doing the same thing here. Instead of writing, look, if I extend this, basically I have mu1 minus mu2. But mu1 minus mu2 is 0. It's the same as we are using h dot. So when mu1 minus mu2 is 0. Why is it 0? Because the assumption is we always go with something that it's not affecting, no difference, status quo. But we design an experiment to prove that that status quo is not the correct one. Status quo, it means that it is both have the same population mean. That means mu1 minus mu2 should be 0. That is what it is, no difference. So an h sub a is going to tell us whatever the experiment is, it will tell us either greater than 0, less than 0, not equal to 0 for h sub n. Again, when you compare here, this is x bar. This is the difference between two x bars. This is s. I can rewrite this one as x bar square root of s squared over n. This is the same as this one. I just took the s inside the radical or square root, but I have to square it. And here we extended that. Again, s1 squared over n1 plus s2 squared over n2. It is the same thing. So this is the t-test. Remember we had z-test, t-test for single, for one sample. This is for two samples. T-test for two samples. Okay. Let's see what the problem is asking us to do. It says, referring to the situation from example 1, are there significantly higher grades when students get a well-balanced breakfast? Well-balanced breakfast. Let's calculate that. So what we have, so now we can write. We know that H0 is going to say no difference. Always we go with the no difference. H sub A, what does it claim? It's claiming higher grades. So that means that mu1 is better than mu2, right? So there's a difference. And the difference is greater than 0, not less than 0, rather than greater than 0. So remember here, purposely, we have to put mu1, which is group 1, which is the ones that they eat well-balanced breakfast, minus mu2, which is less wholesome, and that's the way we have to write the difference. And based on that, we should write the difference exactly the same with this. We have to be consistent. If you say mu1 minus mu2, here has to be x1 bar minus x2 bar. I mean, if you're not consistent, you're going to end up having negative t. And having negative t, it's not a big deal because you can drop the negative and look it up on the table. It's the same thing. So the null will always be 0 because we will always be expecting no difference. Or is that just no? It is true for all of the null hypotheses. You always shoot for no difference, status quo. Nothing is the most conservative case because the assumption is what's out there, you're accepting that. Now someone comes along and say, hey, if you do this experiment, you're going to reject that. And then you're going to try to do the experiment, whether you're going to reject it or fail to reject it. Always null hypothesis deals with the equal sign. Whatever the equal sign is, whatever the norm is, whatever the no difference is, whatever, it's out there. It's given to us from experiments, from years of collecting data. We know that's there, and we take that one as null hypothesis. All right, so let's move on to this. Since this says higher grades, that means well-balanced food is going to give them higher grades. That's the reason I put greater than. If it would have said here that there will be differences, that would have been not equals 0. But that's not the case. Or if it would have said that they will get lower grade, that would have been less than 0. But in this case, that's the case. From here, you can see that mu1 is equal to mu2. From here, mu1 is greater than mu2. It's just a mathematical formula. Bring it to the other side, you can rewrite it like this. Mu1 greater than mu2. So, what is the degrees of freedom? We said that degrees of freedom is the F is 46. We have that. Now we want to, it's just the information I'm putting there. So now what I want to do, I want to calculate the t statistic, right? Because that's what we want to do, t-test. T is equal to x1 bar minus x2 bar. And then you have s1 squared over n1 plus s2 squared over n2. Let's plug the numbers there. So you have 3.2 minus 2.8 comes from this. We gather that information there. Again, you have S1 squared is 0.77 squared divided by 51 sample size plus the other one is 0.436 squared divided by sample size is 47. And if you do this calculation, you have 0.4 divided by 0.13518, and if you simplify this, you get 3.195. That is a t-value. From this t-value, you want to get the p-value. It's the norm. It's in the same thing we have been doing since we learned something about z distribution and t distribution. We are doing exactly the same thing. There are two statistical inferences. One is the confidence interval, and the other one is null hypothesis test. And for all of them, the same thing. Only difference is, sometimes sigma is known, sometimes it's not known, sometimes you have two samples, sometimes you have one sample. That is the difference. Procedure, the whole thing is going to be the same. Okay? So we need to know what this value is. If you want to, again, if you want to use this t, okay, we're going to use the table again to find that value. But before we do that, I want to just mention that you can calculate this, use the Excel. In Excel, all you need to do, because when you look at the curve here, this is the t is going to be here. Okay? This one. So in order to use the Excel, in Excel you need to, you have to type t.dist. And there it's going to give you some values about x bar. Your x bar is the difference now. It's going to be 0.4. Just want to pay attention. Your x bar is not a single value, it's a difference. So here you have to put 0.4. And then it has other stuff. I don't remember what it has, but anyhow, all I'm saying that then degrees of freedom, you got to put the degrees of freedom, and then probably cumulative, you got to put the cumulative value there too. And then when you do that, you should get this answer. You should get the answer that we are going to get from here for the p-value, because this is going to give you the p-value, but we are going to find the p-value from that t-value. Okay, let's look at it here. First of all, is this a one-sided or a two-sided? One-sided, right? You can see that it's greater than. So it's going to be one-sided. So I'm going to look at the one-sided part, that part, right? One-sided. So what do we have? So our degrees of freedom is 40, because we said that we don't have 46. I'm going to put on 40. That's degrees of freedom, 40, right? And we are looking for, what's the number? The number is 3.195. So here, 3.195 lies between these two numbers, doesn't it? You see that? Here is the 3.195. Lies between 2.971 and 3.307. 3.195 is less than that, greater than that. Therefore, it's between those two numbers. If that is the case, so we are going to look at the p-value. So the p-value would be between those two numbers. Exactly. You just come down here. because it's a single value p-value we're calculating, because the mu 1 minus mu 2 is greater than 0. That means single value. So we just drop it down, and then the p-value lies between those two numbers. That's all we can say. If you use Excel, what I showed you, like use a t-distribution, you are going to get a number between these two. It's quite interesting. If you do that, you're going to see that, you know, how beautifully you get that number. It has to be between these two numbers. Okay, I'm going to do this a little bit here. For those of you who might have some problems, this is df. Again, you have 40 here and then 50 here. Since you don't have 46, you're going to go with 40. No 46 here. So you're going to go with 40. And when you go with 40, so you see a number here. This number is 3.195. To the right of this is number is 3.307. To the left of this, there's a number. There's a number to the left of this, and that is 2.971. And this is the number that we calculated from here. So therefore, if you drop down all the way down here, and this is your p-value here. And if you look at it, this row, this is the row for, what do they call it? One-sided p. One-sided p. If you look at it here, you see the number is 0.005, and this number is 0.001. 0.0025. I'm sorry, this is 0.0. Cross it out so many times. It's 0.0025. And that's 0.001. So the conclusion would be my p-value is lies between less than 0.0025 greater than 0.001. Try this, use that when you get a chance, use the Excel, put this value there. If I get a chance, if I finish this lecture, this chapter, I will go ahead and show it to you, but you can do it yourself too. All you need to do, put the equal sign, t dot this, and put the values there. Remember, the values are going to be the difference. Don't put single one up, the difference. Okay, so since this value, basically, this is like a 0.25%, this is like 0.1%, they're very small, right? So we can say there is significant evidence there is significant evidence that GPA of well balanced breakfast group is high. So therefore, from here you can send it to the population. Therefore, that happens to the population. Higher. Okay? All right. Okay. Now, again, in previous chapter, we talked about robustness. Robustness means that, as I mentioned last time, out of the blue, something happens to your system. If your system is robust, it's gonna operate. It's gonna work. That means, like, if something out of ordinary happens, your system's still gonna work. As I mentioned that, like, for instance, if you're building an airplane for, I don't know, for temperatures minus 50 degrees, if you go places colder than that, if it's a robust engine, that means it should work in those areas too. If you go in higher atmosphere, which is temperature drops, so it has to work there up to some point. Like maybe minus 70 degrees should work too. You say that engine is robust. Okay, for any design, even electronics, mechanical, or anything, even in business or in psychology, anytime when you're analyzing a system, you're coming up with some kind of a design for that system. Your design, you want to look at your design to see it's robust. If something happens out of ordinary, does your system give you the right answer? At least, or up to some degree, give you the right answer. Okay, so let's go with this robustness of the two sample t-test. So assuming that it has to be SRS, we always assume that two sample t-tests will give valid results if there are conditions. In the previous one, we said n should be greater than 5. Here we are saying both of them should be greater than or equal to 5. If both of them are greater than or equal, both samples should be greater than or equal to 5, and the distribution are similar, then in shape basically, and sample sizes are about the same. That means like one might be like the way we had it previously, 51, and the other one 47. They're almost the same. But you don't want to compare something with like a 10 as a sample size. The other one is going to be 98. That's a little bit far-fetched. You can't say that. Okay. So if that is the case, you want to have both of them, the summation of n's should be less than 15. Distribution for both data is roughly normal. You don't need to have outliers and so forth and so on. We're going to see that. Here, B, if between 40 and 15, both data sets are slightly or moderately skewed, that's okay, but contains, here you don't have no outliers either. Because this condition is inferior to this condition. So no outlier here, no skewness here, no skewness. Here, if the number is higher between 15 and 40, then you say slightly or moderately skewed is okay, but still you're rejecting, you say that there shouldn't be any outliers. And the last one, if the total of those two numbers greater than 40, anything is acceptable. You can do that. Any kind of distribution works. You can use t-distribution. If the sample size of those two. Again, just make sure that n1 and n2 should be greater than 5, and you're following this information. Provided that if this is 3, that doesn't work here. This would be 3, the other one would be 37. It doesn't work. Okay, let's do one more example here. You can see the effect of two sample, two means, two t-tests. Here what we have, school pride can be measured by a self-report inventory in which subjects record a numeric value for a variety of questions. Two groups of students from different public universities responded with numeric values on a scale of 1 to 5 of the agreement with the statement. When I tell someone where I attend school, I feel a sense of pride, with 1 being strongly disagree and 5 being strongly agree. Data from several of the students at each school are given below. So this is Math University, Math State University. This is University of Monia. Okay. Well, we have these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So N1 is, let's call this one group 1, sample 1, G1, and G2. And N1 is 12 and N2 is 12. So from here, degrees of freedom is both of them 12, subtract 1, pick 1, 11. All right, the next is make a histograms of each group's agreement values. Do you want me to draw a histogram or you're okay, or do you want me to go through that? Yes, no? Okay, yes, we'll do it. That's okay. So let's do it. So this is going to be for group 1, G1, and let's see. So we have, what do we have? We don't have 1 here, right? We'll start from 2, then 3, then 4, then 5. Okay? So we are counting the numbers. This is going to be, here's the numbers are going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay, well, we have, this is the sample size, the width, class, you know, in Excel, we do this. So what we have, we are counting number of students here. They said something 2 or less than 3. Let's see how many of these we have. So we have 2 or less than 3. That would be 1, 2. We have 2 of them, right? So therefore, that would be 2. Now, between 3 and less than 4, so that means you're calculating to see how many 3s are there. 1, 2, 3, 4, 5. So you have 5 of these here. And this one too. All right. And you want to see how many of them have 4 less than 5 or 4. So you have 1, 2, 3. So that goes up to, okay, that is 3 we said. And then you want to see how many 5s. 1, 2. All the way to 6. 6, there is no 6. So you have 2 of them, right? Did we say 2? Yes. That would be. This is for group 1. So we're going to do the same thing for group 2. 1, 2, 3, 4, 5, 6. And this group starts with 1. So we are going to start from 1, 1, 2, 3, 4, 5, 6. So let's count. How many do we have? How many 1s do we have? It's greater than 1 and less than 2. 1, 2, 3. So we have 3. Then how many 2s we have? Oh, less than 3. So we have 1. We have 1, 2. Okay. How many 3s do we have? We have 1, 2. Okay, what did we count? 3, 1, 2, 3, 4. So we have 4 of these. And how many 4s do we have? 1, 2, 3. We have 3 of those. And how many 5s do we have? We have 1, right? I can see something like this as some kind of normal. Not exactly, but kind of. That's going to be 2. Okay, let's see what the question is. So that is the histogram. Are the conditions met for strict adherence to the t-test guideline? Does the robustness of the two sample t-tests imply we will get valid results anyway? That's the reason we wanted to know. So we can see that's normal, almost normal. We see that, what else do we see? We see N1 plus N2, it's 24, right? And 24 is between 15 and 40. That is part of the robustness. Okay. So 24 lies between 40 and 15. There's no outliers, no outliers. What else? I don't think this is skewed. Do you think so? Even if it's skewed, it's nice. So I don't see that. Here might be a little bit to that, but I would say no or just little units. And so we can use a t-test, right? There is one problem we didn't mention. If you look at it here, I didn't see it. Maybe I missed it. I don't see it. This test is not, at least it's not SRS. I mean, the assumption is we got to assume that SRS. So if it's SRS and all those things are happening, therefore this is a t-test. Our answers are going to be valid. Okay, know what skewness? You don't see it, do you? I mean, if this column was high here, it was a little bit to the left of that, but overall, I can see this is the same height, this and that is a little bit skewness. I don't see that even. What did you write after no outliers? No outliers. No outliers, no or little skewness. No or little. I would say no or little. I mean, I don't see it here. You might say something there, but it's small, even if its skewness is small, very small. Okay, are we okay with this? Okay, let's move on to the next. Are we okay with this? Is little, 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 small. Okay, let's move on. Now, find 99% confidence interval for the difference of mean measures of school pride at the two universities. Now, this is a little bit of, you gotta, so if you want to find confidence interval, what is it? CI, I'm going to write the formula again. So we should know by now what it is. x bar 1 minus x2 bar plus or minus, you have t star, then you have square root of s1 squared over n1 plus s2 squared over n2. So let's write the information here. What was the information? We got to find x1 bar and x2 bar. So you know how to find x bar, right? So x1 bar is add them up, divided by 12. Same thing with the lower part. And I got that, I have that x bar is equal, x1 bar is equal to 3.416. For the second thing is x2 bar calculated as 2.83. Now you got to find standard deviation. S1 is 0.996. S2, so this one is 1.337. Again, for standard deviation, do you recall that standard deviation general formula is 1 divided by n plus 1? Then you have, what do you have? You have x bar 1 minus x1 squared all the way to 12 of them. X bar 1 minus x12 squared. Close this, take square root of that. That would be standard deviation. For group 1, you do the same thing for group 2. That's how I ended up getting. Actually, I put this one in Excel. Excel gives it much quicker. Okay, and the size n1 is 12 and n2 is 12. So let's calculate this. And the degrees of freedom is, we calculated degrees of freedom is 11. So if we have 99% confidence interval and degrees of freedom is 11, so what do we have here? This is degrees of freedom 11. This is 99% confidence interval. You see that? That is 3.106. 3.106, 3.106, 3.106, 3.106. Again, if you put that one in t.inv, and here is 99%, that means you have 0.5% on one side, 0.5% on the other side. So this would be 0.995. And then degrees of freedom would be 11. If you put it in your Excel, this is what you should get. You get this number, close to this number or this number. All right, now we got to calculate this. We have all these values. So CI would be equal to X1, that would be 3.416 minus 2.833 plus and minus, and we found this 3.106 times square root. I'm going to write it here. S1 squared, that's 0.996 whole squared divided by N112 plus S2, that would be 1.337 squared divided by 12. And if you simplify that, CI is equal to minus 0.914114 and 2.0783. That is the confidence interval. All right. Okay. Let's do the other problem. Okay, everyone is okay? Okay. Let's do the, good, thank you. Let's do the second one. Next one. The following is a random sample of two groups of students who took the math SAT test, one with coaching and one without coaching. Those are the two conditions. The students took the math SAT twice. All of them, they took it twice. The coached group 400 of 427 received a sample mean of 500, standard deviation of 92 on the first try. The uncoached group of 2,733 students received a sample mean of 506 and standard deviation on the first try. So let's elaborate this a little bit. So I'm going to write coach. This is the coach for both of them, right? Coach for G1. Isn't one coached? So one is coached, one is, so this would be coached G1, group 1. And X1 bar is equal to coach group 427 received a sample mean of 500. That's 500. Standard deviation for this is 92. What else? N1 is 427. That's sample size. For group 2, uncoached, is this G here? Be coached. So uncoached, G2. And the information for them is you have X2 bar. So you have uncoached group of 2,733 students received a sample mean of 506. Standard deviation is equal to 101. Size of the group is, they're the same match, right? N2 is 427. Okay, that is the information we have. Now, for the first one, on the second try, oh God, we're gonna write this too. Let's see. I think this deals with this one. Let's see. Then we'll get to the next one. Is there a significant difference in scores between coached and uncoached students on the first try? Yes. This is the first try. This is the information we have. Is this a two sample or a matched pairs test? Okay. What is it? Is it a two sample or matched pair? How many do we have here? We have the same. Oh, yeah. Thank you. I was going to say matched, but I saw a big number there. 2, 7, 3, 3. Yes, when you look at N1 and N2, so this is not there because N1 is not equal to N2. So it is two sample test. Yes, yes. Thank you. Okay. Remember, this was for the first try. Let's write here first try. But there is another one. It's a different story. We'll get there too. But let's do this one. So what do we have here? So again, the idea H null hypothesis is, since it's two samples, we are looking at the difference in mu's. So mu1 minus mu2 is equal to 0. That means the idea is you don't see the difference, no difference. Or you can say mu1 is equal to mu2. Alternative hypothesis tells us that mu1 minus mu2, what is it? Is there a significant scores between coach and coach on the first try? Difference, significant difference. It doesn't say which one is greater or which one is smaller, right? So it says, is there a difference? So therefore, this would become not equal to 0. There's a difference. I don't know which one is greater than the other one. Or you can say mu1 is not equal to mu2. There's a difference. All right? So we got to write now, if you want to find the confidence interval, I need to know what the t-value is. It's the same as before. So t would be equal to, we have again, x1 bar minus x2 bar. Then you have, basically you have mu1 minus it, that's 0. mu1 minus mu2, that's 0. And at the bottom, you have s1 squared over n1 plus s2 squared over n2. You got to simplify this. So x1 is 500, x2 is minus 506, right here, divided by square root of s1 is 92 over squared over n1, 427, plus s2 is 101 squared over 2,750. And the whole quantity is down here, it's under the square root here. Yeah. So if we simplify this, we get minus approximately minus 1.236. Remember, if you would have switched this, this would have been positive here. If you would have said that x2 minus x1. But no worries, we'll take this one, and I'm going to change this now to positive. The reason I'm changing it to positive because there is no negative numbers here. All I have to do, positive is the symmetric of that, the other side. Remember, whatever you have here, this is T positive, this is T negative here. So instead of looking at here, I'm going to look at there. There's no difference. All right, let's see. So if you want to look at this, what are the degrees of freedom we said? Okay, what is the degrees of freedom here? So between 2,733 and 427, we're going to subtract one from here. This is much smaller than that. So I'm going to take 426 degrees of freedom. So we got to find here degrees of freedom, 426. And the confidence interval is, what are we looking at? A confidence interval. Is there a significant? Oh, we are not looking at. We are looking at the T. I'm sorry. I haven't slept enough last night. But anyhow, so we're going to look at this. So what do we have here? We have if you look at the degrees of freedom, what do you see here? What do we see here? It's almost time. Let me just quickly mention this. We'll finish this on Wednesday. When you look at here, you have the degrees of freedom 426. You can see that it's between 100 and 1,000. So you can't pick 1,000, you got to pick 100. So 100, you're going to draw this line, and then you're going to look at 1.23. So therefore, this would be 100. You see it? I'll go through this on Wednesday too. But that should be 100, and the t-value is 1.236. 1.236, 1.236. It will be between these two numbers, right? It will be between this and that. So therefore, if you drop down here, you're going to look at the double-sided. So it will be between 30% and 20%. I will take the rest of it. Well, we'll do the rest of it on Wednesday. Thank you, folks. Have a great day.